All right. Now let's look at a chi-square test for independence, where we're looking to see if there's a relationship between the sex and the IQ of children who are 10 years old. And we've categorized each different group based on their sex and their IQ. So if they have an IQ less than 85, they're in the low group. And then we had 18 boys with a low IQ and 12 girls with a low IQ. And total, 30 people with a low IQ, 30 children with a low IQ. Average was classified as between 85 and 115 on the IQ test. So we had 47 boys with an average IQ and 54 girls with an average IQ, and a total of 101 people or children with an average IQ in our sample. High was classified as an IQ score greater than 115. 20 boys had a high IQ, 14 girls had a high IQ, 34 total children in our sample with a high IQ. Then if you go across this way, we had 18 plus 47 plus 20 equals 85 boys, and 12 plus 54 plus 14 equals 80 girls. So just kind of breaking down the data for you so you understand what these numbers represent. And we want to know if there's a significant relationship between sex and IQ, or in other words, do sex and IQ appear to be dependent? So you see the hypotheses down here. So the null hypothesis saying that the distribution of IQ scores is not significantly different for males and females, meaning there's no significant relationship between IQ and IQ and sex are independent. Then the alternative is very similar. It's just saying that it is significantly different, there is a significant relationship, and they are dependent. Okay, so let's go ahead and figure out what is our criteria for significance. What is our critical value? So step 2, chi-square crit. So we know that the alpha level is 0.05. And our degrees of freedom is equal to C minus 1 times R minus 1. C representing the number of columns. So how many different levels of IQ do we have? We have 3. So 3 minus 1. And then R represents rows. How many different levels of sex do we have? We have 2. We have boys and girls, and 2 minus 1. So 3 minus 1 becomes 2. 2 minus 1 becomes 1. 2 is our degrees of freedom. So with a chi-square crit, for degrees of freedom 2 and an alpha of 0.05, we already found that for the previous example, and it's 5.99. All right, let's do our calculations. So this is going to be somewhat tedious because there's so many groups. And so we're going to still have to, sum up all of the FO minus FE squared divided by FEs, but we're going to be doing 6 of those this time instead of just I think we had 4 in the last example, or just 3 actually in the last example. So this is going to be a little bit more challenging. Okay, so we want to make sure that we have an equal proportion of girls and boys in each IQ group to test this null hypothesis, that there is an equal proportion of girls and boys in each IQ group. So if you think about it, if 30 out of, and we have a total of, so 80 plus 85, 165, 30 plus 101 plus 34 also equals 165. So if 30 out of 165, or, let's see, 30 divided by 165, P equals 0.182, or 18.2%. So if 30 out of 165 children in our sample, have a low IQ, that means that 18.2% of our sample has a low IQ, and we would expect that 18.2% of the sample of boys would have a low IQ, and 18.2% of the sample girls would have a low IQ. Let's go ahead and figure out all these proportions. So then for the average IQ, 101 divided by 165 gives us a p-value of 0.612, or 61.2%. So 61.2% of our sample has an average IQ. So we would expect that to be equally distributed across boys and girls. So 61.2 of those 85 boys would have an average IQ, and 61.2 of those 80 girls would have an average IQ. Now we also know that 34 out of 165 children in our sample have a high IQ, and 34 divided by 65 gives you a proportion of 0.206 or 20.6%. So if there's no relationship between sex and IQ and the null hypothesis is true, we would expect that 20.6% of those 85 boys would have a high IQ and 20.6% of those 80 girls would have a high IQ. So if we are using the PE times N for the sample, we could find these expected frequencies. So we could say, all right, I'm going to go ahead and recreate this table. So these are our FOs still. These are observed frequencies in our sample. Now we're going to create a table for our FEs. So we've got boys, we've got girls, we've got low, we've got average IQ, and we've got a high IQ. All right. Now it really becomes important to stay organized for this kind of chi-square because we've got so many values to work with. All right. So for boys with a low IQ, if 18.2%, so this represents low, average, and high. Remember? So if 18.2% of our sample has a low IQ, and we expect 18.2% of boys and 18.2% of girls to have a low IQ, we could find that by saying, all right, 0.182 times how many boys? 85. And then 0.182 times how many girls? 80. So under the null hypothesis, we would expect that 15.47 boys would have a low IQ, and I'm sorry, 15.47 boys would have a low IQ, yeah, and then 14.56 girls would have a low IQ in our sample. Now we need to figure out what is 61.2% of the boys and 61.2% of the girls based on the average IQ. So 0.612 times 85 boys and 0.612 times the 80 girls. So under the null hypothesis, we would expect that 52.02 boys would have an average IQ and 48.96 girls would have an average IQ. And you can see that consistently the number associated with boys is higher than the number associated with girls because we have more boys than girls in our sample. Now let's look at the high IQ. So we're expecting that 20.6% of boys and 20.6% of girls will have a high IQ if it's an equal proportion across the entire sample. So 0.206 times the 85 boys and 0.206 times the 80 girls. So under the null hypothesis, we expect that 17.51 boys will have a high IQ and 16.48 girls will have a high IQ. Now I fully recognize that we're working with discrete variables. Frequencies are discrete, and we have decimals here. So that's kind of off-putting, right? It's kind of confusing. It's like, what is going on? Well, for the purposes of testing a hypothesis, it's perfectly okay to have decimals in your expected frequencies column. It's totally fine. Now to kind of double check your work, you want to add up your frequencies for your columns and your frequencies for your rows to make sure that they still are within rounding error of your observed frequencies. We're basically taking this 85 and redividing it up, right? Based on equality across the different IQ groups. But we should still be able to add these up and have the same number of boys under our expected frequencies and add these and have the same number of girls. We should also be adding these and have the same number of low IQs, adding these have the same number of average, and adding these and having the same number of high IQs under our expected frequencies. All right, I'm going to make this a little smaller here. So if you add up 15.47 plus 52.02 plus 17.51, you still have 85 boys. If you add 14.56 to 48.96 to 16.48, you're still working with 80 girls. If you add 15.47 to 14.56, you're within rounding error of 30. If you add 52.02 to 48.96, you're within rounding error of 101. And if you add 17.51 to 16.48, you're within rounding error of 34. And if you add these together, you still come up with the sample size of 165. So when you're doing your work for this, check your work. Make sure that when you add your frequencies expected, either based on columns or rows, that you have the same frequencies in your margins, or at least within rounding error. Now, this strategy for finding FE is very complicated. I don't like it. FE is complicated with this strategy here. Luckily, there's a formula that you can use that simplifies this process. Now, I showed you this formula first because I want you to understand that we're basically figuring out the total proportion of people in our sample with each different level of Y, and then equally distributing X based on those proportions of Y in our entire sample. So a nicer, cleaner version of the way to find the frequency expected, and remember these are our frequencies observed, is to take the frequency for your column, multiply it by the frequency for the row, and divide it by the sample size. Some people prefer the other method. I prefer this method, so I'm showing you both. Okay, so when I talk about frequency columns, these are frequency columns, and these are frequency rows. The boys versus girls, that is the basis for rows, and then the IQs are the basis for columns. So what we're going to do is for each group, we're going to multiply the frequency for the column that group is in by the frequency for the row that group is in, and divide by the total sample size, which in this case is equal to 165. So let's go ahead and get organized, and let's kind of recreate the structure of that table for our frequency expected. So we've got boys, and we've got girls, and we've got low IQ, average IQ, and a high IQ. Okay, so for the boys with a low IQ, we're going to do that one first. And let's see, we have 30 children with a low IQ times 85 boys divided by 165 sample size. So 30 times 30 times 85 is 2,550. Divided by 165 gives you 15.455. Now for the average IQ, well, let's go ahead and do the girls with the low IQ. So for the girls with the low IQ, we have 30 children with a low IQ multiplied by 80 girls divided by 165. So that becomes 2,400 divided by 165. And we are expecting 14.545 girls to have a low IQ in our sample if we have no relationship, roughly that amount. Okay, now let's look at the average IQ boys. So now we have 100 children with an average IQ times the 85 boys divided by the sample size. So this becomes 8,000, let's make that more of a dot there, 8,585 divided by 165. And under the null hypothesis, we're expecting 52.03 boys to have an average IQ. Let's underline these values. All right, let's move on to girls with an average IQ. So 101 children with an average IQ in our sample, multiplied by 80 girls, divided by 165 people in the study. 101 times 80 gives you 8,080, divided by 165, and you end up with 48.97. So under the null hypothesis, we would expect 48.97 of the girls in our sample to have an average IQ. Now let's move on to the high IQ. So 34 children had a high IQ. We have 85 boys. So that becomes 2,890 divided by 165. And we expect 17.515 boys to have a high IQ. Now let's look at girls' high IQ. So we have 34 multiplied by 80 girls divided by 165. That becomes 2,720 divided by 165. And we are expecting 16.485 girls in our sample to have a high IQ if the null hypothesis is true and there's no relationship there. So let's go ahead and chart this out. Just because it'll help us when we're doing our calculations. Now, if you look and you compare the frequencies expected with this strategy to the frequencies expected with this strategy, there are slight differences due to rounding error. But overall, you'll still find that when you add up the frequencies, you're going to get something that's very close to the frequencies that you see in the margins up here for the observed frequencies. So 15 plus 15.455 plus 14.545 is 30. 52.03 plus 48.97 is 101. 17.515 plus 16.485 is 34. Add these numbers together, you get 85. Add these numbers together, you get 80. Add all the numbers together, and you end up with 165 still. All right, let's go ahead and get to these chi-square calculations. Hopefully we have room, because it's kind of a beast. All right, so chi-square is equal to the sum of each observed frequency minus each expected frequency squared divided by the expected frequency. So we have 18 minus 15.455 squared minus 15.455 plus, so now that's for the boys with a low IQ. Now moving on to the girls with a low IQ, 12 minus 14.545 squared divided by 14.545. Now moving on to the boys with an average IQ, 47 observed minus 52.03 expected squared divided by 52.03. Now the girls with an average IQ, so 54 observed minus 48.97 expected. 48.97. And now we're moving on to the boys with a high IQ. So 20 minus 17.515 divided by 17.515. And then finally, girls with the high IQ, 14 is observed minus 16.485 expected squared divided by 16.485. Now, hopefully you know exactly where these numbers are coming from. They're coming from these two tables. And now you can see why it's so important to stay organized, right? This is kind of crazy. Okay. So let's go ahead and start solving for what's inside the parentheses. So for each one, I'm going to do that. And we end up with 2.545 squared divided by 15.455 So that's 18 minus 15.455 is 2.545. And I'm just going to go through and do all of these. So then we have negative 2.545 squared divided by 14.545 plus negative 5.03 squared divided by 48.97. Oop. I think I got ahead of myself there. Okay, so now we're on the third group. Okay, so negative 5.03 squared divided by 52.03 plus 5.03 squared divided by 48.97 plus 2.485 squared divided by 17.515. Finally, negative 2.485 squared divided by 16.485. Woo! All right, now we're squaring all of these values. So we end up with 6.447 divided by 15.455 and 6.447 divided by 14.545. And then we have 25.301 divided by 52.03, and then 25.301 divided by 48.97, and then 6.175 divided by 17.515, and then finally 6.175 divided by 16.485. So you can see that even these negative values became positive once we did the squaring, right? And let me make these equals red so it's pretty clear, like each different step of the way. Okay. So now we do all the division and we add together. So we end up with, finally, 0.419, 0.419 plus 0.445 plus 0.486 plus 0.517 plus 0.325 plus 0.375 and a chi-square of 2.567. Woo! For those of you who enjoy calculations, this is the chapter for you. Oh my goodness. So 2.567 is our observed chi-square. And 2.567 is not greater than our critical value of 5.99. So for step 4, after all that, we fail to reject the null hypothesis, and we would state this as our conclusion. Now, you don't have to state all of those. You could say the distribution of IQ scores is not significantly different for males and females, or you could say no significant relationship between IQ and sex, or you can say IQ and sex are independent. That's totally fine. Any one of those is fine. I prefer the no significant relationship between IQ and sex because that really helps you understand that this analysis is pretty similar to correlation. Now, I want you guys to try the next example, but I would just recommend that you only stick with doing this formula to find your expected frequencies. That's the formula I'm going to use. I'm not going to go through the more conceptual formula of, what percentage is each group for Y, and then using that to calculate your frequency expected for each group for X. Go ahead and use this formula to find expected frequencies and try this problem on your own. So pause this video and give this problem a shot. All right, so now we're doing another chi-square test for independence, and we're looking to see if there's a relationship between whether or not children had pets at home and if they had allergies. And we're specifically looking at the number of cats or dogs. So we've got children who had, or people who had 0 dogs or cats as children that had no allergies in college, people who had 1 dog or cat as a child with no allergies in college, people with 2 or more dogs or cats as a child who had no allergies in college, and then those who had 0 dogs or cats had allergies, 1 dog or cat, allergies, 2 or more dogs or cats, and allergies. So in our total sample, 90 had no allergies, 30 had allergies, 40 were raised with no cats or dogs, 60 were raised with 1 cat or dog, and 20 were raised with 2 or more cats or dogs. 40 plus 60 plus 20 is 120, 90 plus 30 is also 120. So the null hypothesis, and I'm just going to stick to the one I prefer for this one, there's no significant relationship between having animals as a child and resistance to allergies. Whereas the alternative would be there is a significant relationship between having animals as a child and resistance to allergies. So I didn't really mean for this to happen, but it just kind of works out that once again, we have a chi-square crit of 5.99 because we have an alpha level of 0.05 and degrees of freedom equal to C minus 1 times R minus 1. We have 2 columns, so 2 minus 1, and 3 rows. This becomes 1 times 2. 2 is our degrees of freedom, and so our chi-square crit is still 5.99. And like I mentioned in the conceptual lecture, we still have our independent variable here and our dependent variable here, right? We think that having allergies depends on whether or not you had pets growing up. All right, so let's go ahead and do our crazy calculations for step 3, finding that chi-square statistic. All right, so let's go ahead and recreate this table. So we've got 0, 1, 2 plus. And then we have no allergies and allergies. Okay, so for this first one, we are going to remember our expected frequencies is equal to the frequency for the column times the frequency for the row divided by the sample size. So for no allergies, 0 cats or dogs, the frequency for that column is 90. The frequency for that row is 40. So 90, 40. And the sample size is 120. So 90 times 40 is 3,600. Divided by 120. And we get 30. All right, so for the next group, so no allergies, 1 dog or cat. The column total is still 90. The row total now is 60. And we're dividing by the sample size of 120. 90 times 60 is 5,400. Divided by 120. 5,400 divided by 120 is 45. Next group, no allergies, 2 or more cats or dogs. So 90 times 20 divided by 120, we have 1,800 divided by 120, and we get 15. Okay, now let's look at the next group. And you can notice that for all of these groups in the same column, they have the same column total of 90 with different row totals. All right, now let's look at allergies, no cats or dogs. So we have 30 is the column total times 40 is the row total divided by 120. 30 times 40 is 1,200. Divided by 120, and you get 10. Next group, allergies, 1 cat or dog. The column total is 30 times the row total is 60 divided by 120. 30 times 60 is 1,800 divided by 120, and you get 15. Next group, allergies, 2 or more cats or dogs. Column totals 30, row totals 20. This gives you 600 divided by 120, and an expected frequency of 5. So if I'm looking at this, I can again see that my column totals are the same for all of these groups because they're in the same column with a total of 30. And then if you look across the rows, the row totals are the same for each row because for this row we're looking at a row total of 40, then a row total of 60, and then a row total of 20 for those groups. Okay, so now we're ready to compute our chi-square statistic using our expected and observed frequencies. So our chi-square statistic is equal to the sum of each observed frequency minus each expected frequency for each group squared divided by the expected frequency. I'm going to kind of fly through these because I'm expecting that you've already done this on your own. All right, so we have 22 minus 30 squared divided by 30 plus 50 minus 45 squared divided by 45 plus 18 minus 15 squared divided by 15 plus 18 minus 10 squared divided by 10 plus 10 minus 15 squared divided by 15 plus 2 minus 5 squared divided by 5. And let's make that equal sign red. Okay. So 22 minus 30, so we end up with negative 8 squared divided by 30 plus 5 squared divided by 45 plus 3 squared divided by 15. So I'm just solving for the parentheses right now. Plus 8 squared divided by 10 plus negative 5 squared divided by 15 plus negative 3 squared divided by 5. Okay. So I'm just going to square all of my numerators now. So negative 8 times negative 8, 64. Divide that by 30. 5 squared, 25. Divide by 45. 3 squared, 9. Divided by 15. 8 squared. So we're basically just repeating what we already had because we have the same values again. Oops. Not all the way, though, silly. Just your numerators. Okay, so we've got 64 divided by 10 plus 25 divided by 15 plus 9 divided by 5. All right, so now I solve for those fractions. So we have 2.133 plus 0.556 plus 0.6 plus 6.4 plus 1.667 plus 1.8, and we get a whopping chi-square of 13.156. That is our chi-square observed. All right. So 13.156 is larger than our critical value of 5.99, so we reject the null hypothesis and conclude that there is a significant relationship between having animals in a child and resistance to allergies. And if we look at our expected frequencies compared to our observed frequencies, so I'm going to go through and circle the higher number for each group. Is it observed or expected? So 30 is greater than 22. 50 is greater than 45. 18 is greater than 15. 18 is greater than 10. 15 is greater than 10. And 5 is greater than 2. Do you see that opposite pattern? So if we are looking at the null hypothesis saying there's no relationship, then 30 of the people with with 0 cats and dogs should have had no allergies. We only saw 22. Then if we look at the people who did have pets, more had no allergies than what we would expect to see if there was no relationship. So just based on that, I'm thinking that having a pet results in more likelihood of having no allergies than what you would expect if having a pet had no effect on having allergies. Now when we look at the allergies people, if having pets did not help you resist allergies, we would expect to see 10 people with allergies for those who had no cats or dogs. We saw 18, so that's more than we would expect. So having allergies is more common than you would expect when you don't have any pets. Then if you look at these numbers, if there's no relationship, then we would think 15 people who had 1 dog or cat and 5 people who had 1 dog or cat would have allergies, but we actually have fewer that had allergies, and that's because we think that the people who had pets were more resistant to allergies than what we would expect if there was no relationship between those two variables. Okay, so chi-square is a lot of calculations, but I feel like most students don't struggle with the calculations as much as with the conceptual piece of this. And as far as the conceptual piece for the chi-square test for independence, it's really similar to the correlation, so it's something you've already been exposed to before.